So as the bed rises, then that brings up the water level, and so every time that happens, you have to adjust how the rating is between the stage and the amount of flow that passes by here.
Our surface water crew has a real challenge at this site because you're exactly right. As the bed rises and the surface of the water rises, the relationship to discharge and water depth changes. So they're pretty much out here constantly measuring the surface of the water and the amount of discharge for any given section.
So that's the water sampler here, automated sampler. Why are these good to have at a site like this?
Well, because none of us like to get up at 3 in the morning and sample suspended sediment. This guy will do it for us based on the stage that we've preset. So with looking at the discharge of the river and what it's done over the past few months, we'll set this thing so that it starts sampling as the hydrograph starts to rise. It'll hit a threshold and then it'll begin sampling every hour. It'll sample for 12 hours and then it kicks back. Usually that's over the top of we've begun the recession side of the hydrograph. Then it'll slow down to every 2 hours. And what that allows us is we've got samples across the hydrograph for suspended sediment. It prevents us from coming out here during unsafe times. It also prevents us from having to be here at odd hours. But in order to make sure that we understand what it's doing and what it's sampling, we're out here at nearly base flow collecting an EWI, an equal width increment suspended sediment sample. So that's our gospel. That's the benchmark of what's actually in the river right now. I'm going to collect 2 samples out of this sampler, and once he's done, we're going to collect another 2. And we'll compare those to what he's collected in the river, and we'll have a relationship between what's going on with this machine and what's going on in the river.
And the thing is, this collects from one point where the tube is located in the river, and then
Absolutely.
you want to develop a relationship between that and what's happening across the entire channel.
Absolutely, couldn't said it better. So this is a little noisy, so we'll get started here. This is a peristaltic pump that draws from, as Faith said, one point in the river down there, and will fill about 750 milliliters into this bottle. That's more better.
This is our in-stream sampler for our ISCO at Patapsco at Catonsville, directly below our former SIMPKINS dam removal site. Here what we've developed is basically a meter that can function with our changes in flow. It can rise and lower the stage, and it most importantly keeps our intake off the bed, because otherwise we would possibly start sucking sand and bias our samples that we collect. In addition to our point sampler, we also have a turbidity probe situated directly below it, so as not to influence it, so neither influence each other. And between the two, we'll be able to construct our suspended sediment loads as well as daily values and annual.
The turbidity probe, or nephelometer, allows us to get sediment concentrations, suspended sediment concentrations, when we're otherwise not able to collect samples. So that's kind of like the backup that's there when we're not.
How is this usually done? It's pretty involved, right, to be able to get a good representation of what's coming down the river.
Yeah, what we like to do is we'll come out at least monthly, unless there's a storm event, then it's much more intensive sampling. At low flows we can weight it, otherwise we work from a bridge and we do what's called an equal width increment sample. And the primary purpose of it is for us to use it to calibrate our point sampler. This is a depth integrated sampler, DH81 handheld. Basically what it does is it allows us to get a full profile of our suspended sediment concentration along the reach. We stretch a line, we get an approximate width of or an actual width of the river, and then we break that into about 10 verticals, and we sample the centroid of each vertical.
So get both the depth and the width and across it, and get the right representation of water going through there. So it looks pretty simple design there, but there's a lot of technology really that goes into those, right?
That's a pretty sophisticated piece of equipment, and it's designed specifically as an isokinetic sampler, meaning that if used properly, when it's lowered into the water at a rate no greater than 4/10 the velocity of the water, sediment, suspended sediment and water will enter that nozzle at the same speed that it's traveling down the river. If it goes faster than that and particles accelerate in that nozzle, then you're going to get a biased sample with too much sediment. If it's the opposite and prevents water from entering and suspended sediment from entering, then it's going to create eddies there, slow the water down, and you're going to get bias on the other side. So this is a pretty sophisticated piece of equipment, and if used properly, we're going to get a very accurate representation of suspended sediment in the river. And I think Mike's going to get started now doing our increments. And we've sampled this river a good number of times. If this was the first time we were sampling it, we'd take kind of a sample measurement at the deepest part of the river so that we'd get our transit rate. And that rate is the speed with which we submerge and raise the sampler. Mike's done this enough times that he can do it pretty well by memory. So he's going to start here on the left bank and collect across. Otherwise, we would have started in the center, got an estimate transit rate, and then started here on the left bank.
So the main thing is with the steepest section, he doesn't want to fill the bottle.
Doesn't want to overfill that bottle. That's real important. He can aggregate as many sections as he thinks he should, but what he can't do is overfill the bottle. Then he has to start over from wherever that bottle started. You can see him. He starts right at the water surface. He lowers it at a very even rate, raises it at the same rate, and he'll examine how much he's collected and decide whether or not he needs to change bottles.
Standing behind it, kind of off to the side a little bit, so he's not disrupting the flow of water.
Absolutely, and again, he doesn't want to create an eddy. He doesn't want to create a vortex. And just a little history, prior to the dam being removed, Mike would have been over his head here. So we've had a great deal of accretion on this bed as a result of the removal of the dam.
One other thing too, the way the nozzle is designed on the bottle, it keeps the nozzle just above the bed so that it doesn't hit the bottom or disturb the bottom. So we're just getting that water column part of things. Water looks pretty clear today, but I bet when there's an event, it gets a lot of sediment.
We had an event about a week and a half ago that it'll turn it to chocolate milk pretty quickly. And the materials that we're sampling then, in order to do this sort of sampling at high water, we have to do it off this bridge over here. And we'll do that with a separate sampler, a much heavier sampler, that will remain vertical in the water during these high flows. That particular sampler weighs, I think, about 68 pounds.
So even, you can't really see it because it's underwater, but there's sand moving constantly in the suspension too.
Absolutely. The finer sand portions are in fact being suspended and moved, while the coarser ones are visible moving along the bed. Those two, in concert with something called the wash load, constitute the total load moving downstream. And as we said earlier, once that dam was removed, we placed a lot more sediment in motion, and our goal here is to determine how much of that sediment moves downstream.
You can see the water's pretty clear because we're at base flow. That's what we'd expect to see, but the lab, whenever we get it composited and get stuff back, we'll get numbers on this that our eye couldn't give us.
To calculate our loads, we've got a nephelometer that's measuring turbidity in the water. We have a point sampler, and then periodically we have in-stream samples, equal width increment samples that are our gold standard to calibrate the other measurements by. So we have a well-instrumented site here, and we're collecting a lot of very important data.